Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole, and I'm from Calgary, Alberta. It's episode 10. Double digits, baby. Full disclosure, as something special for episode 10, I had set out to tell you about an engineering marvel, and I still will. But when I started researching, I found all of these smaller failures that I thought you'd want to know about too. So with that said, this week's episode is about the International Space Station. Now, I don't think any of the failures I'm going to tell you about are due to engineering missteps or oversight. We've barely scratched the surface of space exploration. And all things considered, the International Space Station is an extremely impressive human accomplishment. But things still go wrong, especially after 22 years in space. Yes, that's right. Did you know it's that old? Boy, how time flies. Houston, this is Failurology, ready for takeoff. This week in engineering news, transparent solar panels. A study from Incheon National University in South Korea demonstrates the practicality of transparent solar cells. Researchers used a glass substrate with metal oxide electrode, thin layers of semiconductors, and a coating of silver nanowires. The semiconductors were made from titanium dioxide, an environmentally friendly and non-toxic material, and nickel oxide, nickel being an abundant element on Earth that is able to be manufactured into nickel oxide at low temperatures. Both semiconductors have a high optical transparency, meaning they can absorb UV light while allowing most of the visible light through. The solar cell had a power conversion efficiency range of 2.1%. Are you thinking 2.1% is low? Because so did I. But the world record for the maximum power conversion efficiency is only 22.49%. So with that in mind, 2.1% on the first crack at something that's never been done before seems pretty good. And the solar cell still allowed more than 57% of the visible light through the cell. The applications for this research and the advancements that will come from it are endless. Commercial and residential buildings, windows or exteriors, car exteriors, even phone screens. And this is just the beginning. If you want to read more on the study, check out the podcast page for this episode. Link in show notes. Now on to this week's episode, the engineering marvels and incidents of the International Space Station. The station launched on November 20th, 1998, over 22 years ago. It's currently expected to remain in operation until 2030. The station is 73 meters long, 109 meters wide, weighs over 400,000 kilograms, and has a pressurized volume of over 900 meters cubed. Atmospheric pressure is 101.3 kPa and is made up of 21% oxygen and 79% nitrogen. With an orbital speed of 7.66 kilometers per second, it orbits the Earth in just over 92 minutes and completes almost 16 orbits per day. It was constructed and operates in collaboration with space agencies from the US, Russia, Japan, Europe, and Canada. The station's been manned since November 2nd, 2000, with a crew of up to 7. Over 239 astronauts, cosmonauts, and space tourists from 19 nations have visited the space station. 8 of them were Canadian. To mitigate the loss of muscle and bone mass, astronauts work out for at least 2 hours per day. And with the onboard water recovery system, the crew dependence on water is reduced by about 65%. The station's laboratories act as a microgravity and space environment research lab in astrobiology, astronomy, meteorology, physics, and other fields. It also tests spacecraft systems and equipment for future long-duration missions to the Moon and Mars. The station is modular, allowing sections to be added or removed, and operates as 2 main segments: Russian, and everyone else. From the Russian orbital segment, we have the following modules. Zarya, which is a functional cargo block, was the first module to be launched, and it provided power, storage, propulsion, and guidance during the initial assembly. Now it's mostly used for storage. Zvezda, the third model launched, that docked on July 26, 2000, provides all of the life support systems, although some are implemented in the US segment, as well as living quarters for two. It acts as the center of the Russian segment, with crews using this area to meet during emergencies. PERS and Poisk are identical airlock modules, each with two identical hatches. Their outermost docking port allows docking of Soyuz in progress spacecraft and automatic transfer of propellants to and from storage. PERS was launched on September 14, 2001, and is used to store, service, and refurbish Russian Orlan spacesuits and provide a contingency entrance for Americans. Poisk launched on November 10, 2009. Razvet is the mini research module used for cargo storage and a docking port for visiting spacecraft. It was connected to the station on May 18, 2010. In what they refer to as the U.S. orbital segment, which is operated by many nations, there is Unity, the first U.S. module and the second ever module to join the station. It's the connecting module between the U.S. and Russian segments, where crews eat meals together. Unity has 6 berthing locations to connect other modules. Connected to Unity is the Destiny module, launched on February 7, 2001. It's the primary facility for U.S. labs. The research from this facility is used by scientists around the world working in medicine, engineering, biotechnology, physics, materials science, and earth science. Quest, which launched on July 14, 2001, is the primary airlock, hosting spacewalks with extravehicular mobility unit spacesuits, which are US, and Orlan spacesuits, which are Russian. Before then, Russia used the Zvezda module, and US used a dock space shuttle when accessible for spacewalks. Harmony is the utility hub, which connects laboratory modules for US, European, and Japanese labs. It provides electrical power and electronic data, sleeping cabin for 4 crew, and when it was launched on October 23, 2007, it added almost 20% to the station's living volume and rendered the US core complete. Tranquility contains environmental control systems, life support systems, a toilet, exercise equipment, and a dome observatory, and it launched on February 8, 2010. Columbus is the European laboratory, which launched on February 7, 2008. Kibo is the Japanese laboratory and the largest single module. Leonard, installed on March 1, 2011, is used for central storage of spares, supplies, and waste, as well as a personal hygiene area for astronauts in the US segment. And then there's my favorite part, the Canadarm2. It's 17.6 meters long when fully extended. It has 7 motorized joints, 2 end effectors or hands, and a 35 centimeter diameter titanium shaft with Kevlar fabric cladding, capable of handling payloads up to 116,000 kilograms. It can assist with docking and is self-relocatable. It can move to any power data grapple fixture on the station. There are also 12 solar arrays, 2 heat radiators, and a number of other components that serve the station and its guests. With all of the docking segments, 8 spaceships can be connected to the station at one time. There have been 64 expeditions to the International Space Station to date, the latest of which, the SpaceX Dragon, launched on December 6, 2020, arriving at the station just over 24 hours later. It undocked from the station this past Tuesday, January 12th at 7:05 a.m. Mountain Time. It was supposed to undock on Monday, but due to unpleasant weather off the coast of Florida, it was delayed a day. It landed Wednesday night at 6:26 p.m. Mountain Time via parachute-assisted splashdown in the Atlantic with almost 2,000 kilograms of scientific experiments and other cargo. The landing location allows for quick transport of the research to Kennedy Space Center's Space Station Processing Facility. Some of the precious cargo the Dragon is bringing back are as follows. Using 3D engineered heart tissue, Cardinal Heart studies the impact of gravity on cardiovascular cells and tissues. From this study, researchers are hoping to better understand heart problems on Earth, identify new treatments, and improve screening measures to foresee cardiovascular issues prior to spaceflight. Space Organogenesis, a Japanese program, is studying 3D cell growth using microgravity. On Earth, cells require support to expand into 3 dimensions. From this study, scientists are hoping to demonstrate how microgravity can be used for developments in regenerative medicine and creation of artificial organs. The Sextant Navigation Experiment tested specific techniques for emergency navigation on deep space mission aircraft. Sextants have been used by sailors for centuries for navigation. Scientists studied the function of arteries, veins, and lymphatic structures in the eye and changes in the retina of mice before and after spaceflight. 40% of astronauts experience vision impairment on long space flights. A thermal amine scrubber was tested, which contains actively heated and cooled amine beds to remove carbon dioxide from the air on board. CO2 buildup can lead to fatigue, headache, breathing difficulties, strained eyes, and itchy skin. And lastly, an investigation into the growth of biofilm and their ability to corrode stainless steel, as well as the effectiveness of silver-based disinfectant, hopes to provide better ways to control and remove resistant biofilms for successful future long space flights. Now on to the issues, what you all really came here for. The International Space Station definitely has redundant systems, but there's really no backup per se. You have to troubleshoot and repair everything yourself for the most part. Yes, there are spare parts and ground crews that can help, but they can't exactly overnight supplies or call a repairman for you. Have you ever tried to fix something and had to go to the hardware store multiple times? It's always embarrassing when this happens, but I think that most of us have been there. There's definitely no hardware store in space. Now with that said, here are some of the quote-unquote highlights of the system failures on the International Space Station. In 2003, there was waste accumulation after the Columbia disaster. The Space Shuttle Columbia disintegrated upon atmosphere re-entry on February 1, 2003. This resulted in a 2.5-year suspension of the U.S. Space Shuttle program, and then another year after the return to flight mission due to uncertainty in the future of the space program. During this time, crew exchanges were done using a Russian Soyuz spacecraft. Because the International Space Station was not visited by U.S. spacecraft for over 3 years, there was more waste accumulated than expected. A minor leak was detected on January 2, 2004. At its max, the leak resulted in 2.5 kilograms per day of air leaking into space, and the internal pressure dropped from 101.3 kPa to 96.5. The astronauts on board traced the leak on January 10th to a vacuum jumper hose on a multi-paned window in the U.S. segment, and it was repaired. The electron oxygen generator units shut down due to unknown causes. 2 weeks of troubleshooting got it up and running, but then it immediately shut down again. Eventually, they figured out that the cause was air bubbles in the unit, which was not functional until a resupply mission in October 2004, but it failed again on January 1, 2005. On September 18, 2006, fumes from one of the 3 electron oxygen generators in the Russian segment activated a smoke alarm. The fumes were later determined to be a potassium hydroxide leak from an oxygen vent. The station's ventilation system was shut down to prevent potentially spreading smoke or other contaminants to the rest of the complex, and a charcoal filter was used to scrub the air. The electron oxygen generator was repaired on November 2, 2006, with spare parts from a Russian payload. On June 14, 2007, a computer malfunction on the Russian segment left the station without thrusters, oxygen generation, a carbon dioxide scrubber, and other environmental control systems. The primary systems were back online by June 15th, but without the secondary system that controls oxygen levels, the station had 56 days of oxygen left. The malfunction was ultimately caused by condensation inside the electrical connectors, and the computers were all back up and running on June 16th. Plans were implemented to prevent this problem in the future. On October 30th, 2007, after relocating 2 solar arrays to their final position, a 76-centimeter tear was noticed on the second array when it was roughly 80% deployed. A spacewalk, which usually took months to plan, took place on November 3rd. The astronaut rode the end of the spacecraft Discovery's 50-foot boom arm to repair the damage. The repair was also considered to be more dangerous, relatively speaking, due to the possibility of shock from the solar array, using the boom arm, which hadn't been done like this before, and the lack of pre-planning. In 2007, there was a damaged starboard solar alpha rotary joint. Sidebar for a second to let you know about a little memory trick I have. Port and left are both 4-letter words. Therefore, starboard must be the right. That's how I keep track of which is which. But back to the rotary joint. The starboard joint, and a similar one on the port side, rotates the large solar arrays to keep them facing the sun. In October 2007, excessive vibration and high current spikes were noted in the drive motor. Inspection found excessive contamination from metallic shavings and debris in the large drive gear and damage to the large metallic race ring. The joint was locked in place until it could be repaired. In September 2008, the crew cleaned and lubricated both the starboard and port joints and replaced 11 of 12 trundle bearings on the starboard joint. NASA developed a long-term solution to install structural supports between the starboard and port joints and a new race ring between them to replace the failed joint. But they've since found that cleaning and lubricating the joint had great results and will continue to maintain the joints this way until the failure can be fully analyzed. An incorrect command sequence on January 14, 2009 caused the Zvezda rocket propulsion control system to misfire during an altitude reboost maneuver. Vibrations were felt in the station structure for over 2 minutes. Further analysis ultimately determined that the station didn't suffer any structural damage, although initially they had thought some components may have been stressed beyond their design limits. Damage to one of the external thermal control system radiators was noticed in September 2008. The surface of the subpanel had peeled back from the underlying central structure. Speculation is that damage was caused by a micrometeoroid or debris impact, or perhaps a service module thrust cover that got loose during an earlier spacewalk. Although there was no evidence of a leak or even a reduction in the thermal performance of the panel's ammonia loop was closed off from the rest of the system. Imagine driving around in the summer and your AC stops working, except you're in space. You can't exactly open the windows. A failed ammonia pump module knocked out one of 2 external cooling loops and left the station with only half of its normal cooling capacity on August 1, 2010. An attempted replacement of the pump on August 7th found an ammonia leak in one of the 4 quick disconnects. The pump was replaced on August 11th and the loop function was restored. An unidentified object was seen on June 28, 2011, traveling at 47,000 kilometers per hour, 340 meters from the station. The 6 crew members at the station boarded the Soyuz capsule and closed all hatches. They were almost undocked from the station when the all-clear was given and the debris had passed without incident. In late 2011, one of the 4 main bus switching units that routes power from the 4 solar array wings to the rest of the station stopped responding to commands or sending status info. A replacement mission on August 30, 2012 failed to be completed because a bolt jammed before the electrical connection was secured. With the bus switching unit down, the station was at 75% capacity, leading to minor limitations until it could be addressed. If this wasn't bad enough, a 3rd solar array wing went offline due to a fault in the direct current switching unit, further reducing capacity to 5 of 8 solar array wings. Power was restored to the station on September 5, 2012. On June 16, 2012, the main carbon dioxide scrubber in the lab shut down. There was a backup system, but it had issues with sticking valves and the crew only wanted to use it if necessary. The lab scrubber shutdown was traced back to a failed temperature sensor. The crew tried to repair it, but due to erratic data, they decided to run the backup system, even with the sticking valve issues. Then on June 13, 2013, the crew noticed white flakes floating away from the station, resulting from an ammonia leak. In September, one of the sticky air valves was replaced, but the problems persisted, and the standby carbon dioxide scrubber had to be restarted several times. The crew held on to the previously removed valves as backups, just in case more problems persisted, but that was a last resort. A small pressure leak was noticed on August 29, 2018 in the Russian segment. An investigation found a 2mm hole near the hatch of the Soyuz spacecraft. The hole was covered with Kapton tape, which from what I've read seems like space duct tape, and then an onboard patch kit. Neither was a permanent solution, and sealant was later applied to stabilize the station's pressure. And lastly, a higher than normal air leak was detected in September 2019. On September 29, 2020, the leak was isolated to the Zvezda module and an attempt was made to patch it. Another leak in the section has led to consideration to close off this section and use oxygen reserves, but this would impact the entire station. So there you have it. The ups and downs of the amazing International Space Station. Nothing too drastic happened, and no one was hurt. But I'm sure there were still some hairy moments up there for the crew. Not sure if you've seen the TV series Away. In it, Hilary Swank is the commander of a mission to Mars. During the series, they lose the primary water reclamation system, and the backup can't get them all the way to Mars. They come up with a risky plan and ultimately are able to repair the primary system, but not without extensive rationing of water to the crew, leading to extreme dehydration. Yes, this is fiction, and I'm sure there are several inconsistencies about the show. But one thing that I think they got right is that the crew has only themselves and the parts they brought with them to repair anything that goes wrong. And as I mentioned earlier, there are a lot of unknowns when it comes to space exploration, and anything could really go wrong. I visited Houston in 2018 and was lucky enough to take a trip to the Space Center. They have rockets and spacesuits on display, among other things. It was very cool. The Space Center itself is huge, but the public only has access to a small part. One really interesting thing I saw while I was at the Space Center are the number of bicycles around the campus. In 1969, Schwinn donated a number of bikes for employees to get around the station. Whether from your parking spot to your office or from meeting to meeting, there are bikes everywhere. You just grab one that's available and leave it for the next person. I don't know why I found this bike thing so fascinating, but it was very cool. Who goes to the Space Center and falls in love with bikes? I guess I do. Check out the podcast page, link in show notes, for photos from this week's episode. If you're enjoying what you're hearing, please rate, review, and subscribe to Failurology so more people can find it. And if you want to chat with me, my Twitter handle is @Failurology, or you can email me at thefailurologypodcast@gmail.com. Thanks everyone for listening, and tune in next week to hear about the Titanic, the unsinkable ship that sank on its maiden voyage. But more on that next week. Houston, this is Failurology. The Eagle has landed. Over and out.